All right, welcome. Today, we're going to be talking about project management. We're going to be talking about project management for two lessons, for lesson 18 and lesson 19. Today, we're going to start with lesson 19. Start with lesson 18. But before I get to that, I want to talk about the project submission. You all will have gotten your project assignments by this point. And so let's talk a little bit about the project assignment. All right, this is when you've worked on your report, this is what I expect each student to submit. And these will be, two things will be submitted on D2L on a Dropbox that's going to be titled Course Project. So anyway, the first thing is your project report. Your report should be no more than 4 pages, definitely no more than 4 pages to address the problem and answer the questions on the problem thoroughly. This can be preferably in a Word document or perhaps a PDF, but place your report on the Dropbox. Along with that will be any drawings, anything that, or any computations or calculations that you have to support your work that's in the project report. So 4 pages and then followed up by appendix data. And then also if you have done work in Excel or any other software, you need to provide that in a workbook, also at the Dropbox. And I would recommend, this says separate worksheets, but it should be one submission, a workbook with several tabs with worksheets as needed. So the last thing, of course, is I do need those to be neat and legible. Obviously, I can't grade it if I can't read it, and I have difficulty getting back in touch with you. So please, whatever you submit, I will accept handwritten submissions, but they must be neat and legible. So whatever you submit, I have to be able to read. So we'll talk about this more as we go through, and of course, always ask questions if you have questions. Okay, today in this video, we'll talk about project management and CPM, or the critical path method. And this will all become clear as we dive into it. This is out of chapter 9 for both lessons 18 and 19, pages 361 to 399 out of your textbook. And we'll be using examples from the textbook. So let's look what we're going to do. Today, we're going to talk about projects in general. I'll go through several slides really quickly to talk about what projects are. And then we're going to talk more specifically about the critical path method, go through an example. And then I think probably what I'm going to do is I will have a second video separately about project crashing, but it's going to use the same example that we're going to talk about in this video. And then the next lesson will be probabilistic evaluation and review technique, where we have probabilistic activity times. All that terminology will become clear as we move through. So let's go ahead and start talking about project management. First of all, a project is a one-time activity. It can be software development, it can be a product development, it can be building construction, any large project that consists of multiple sequential tasks to accomplish a large activity. It normally involves a team that's led by a project manager, where there's a significant amount of planning that's done in advance to lay out the tasks that need to be accomplished, the deadlines, the budget, all of those different components, materials, laborers, all those detailed things that need to go into the planning of this unique effort. You'll see this all described in greater detail, pages 361 to 370 of your textbook. But it's a one-time, large scale activity with a specific to reach a specific goal or an end state. One of the key aspects of this managing the project is developing the schedule, and that's what we're going to be looking at when we look at critical path method and probabilistic evaluation and review technique. We're going to be looking at how this schedule is managed. Another critical useful way to look at how to schedule a project is using a Gantt chart. And you may have seen this if you've been involved with projects and project management. But the Gantt chart, both the Gantt chart and the critical path method, lay out the activities that need to be accomplished and how long the length of time that those activities take, and then the sequence of those activities. And so in this case, as you'll see, activity A has to be completed before B and C take place. And in the same way, activity 1 has to be completed before 2 and 3. So that's just a graphical representation of the schedule. And we'll look at that more. This is one I wanted to show you just quickly. This is one we actually used in 2014 and 2015 when we were renovating the Coffin locker rooms for our women's volleyball and women's basketball team. Starts all the way from general conditions that have to be taken care of, demo, all the way down to final cleaning and the punch list, things that need to be corrected. So this was actually what we used to manage. We did start in May. We did not complete this until September. So because things happen, things change, materials don't come exactly on time, the schedules get pushed to the right, pushed later in the calendar. But we came together once every 2 weeks to see where we stood, and we were able to adjust and modify and continue the planning. So it's a very useful tool. This is which is a Gantt chart in this case. So the planning, scheduling, and then control. The control is are we on schedule? As I mentioned previously, or are we delayed? What's the risk? Are we within acceptable tolerances? And then, of course, always cost. That project management team comes together to oversee the schedule, risk, and cost to make sure that the project is completed. And again, this is explained in greater detail on pages 371 to 375 in your textbook. All right, next we're going to look at an example that you'll find in page 375 to 383. And this is it's a simple example of building a home, and it's consolidated into 7 different tasks, beginning with task number 1 all the way through number 7, where we design the home and we obtain financing all the way till we finish detail work. This is the first column, of course, is the task number. The second column is a description of the task that is going to be accomplished. And then the third column is the column of immediate predecessors that tells which tasks must follow which. So, for example, task 2, which is lay the foundation, cannot start until the design is completed and the financing is attained. And the same thing is, once you begin to lay the foundation, you can order the materials, but that has to occur after the home is designed and the financing is in hand. So what we say is task 2 is preceded by task 1, and task 3 is preceded by task 1. If you'll see, these two tasks, 2 and 3, can occur simultaneously. So the question is, and then finally, the column 4 is the duration. How long each one of these tasks take? And so the question is, given these durations, and these are in weeks in this example, how long is it going to take to build this house? So, and alternatively, we're going to be able to answer which one of these tasks have to be completed on time, and which tasks are not required to be completed on time. All right. At this point, I want to clarify again a little bit of the terminology, and the term project is the overall completion of all of the tasks. All right, and so that's going to be the overall completion of all of the projects. All of the tasks required in the project. I'll use the term these terms, tasks and activity, interchangeably. So these can be either. These are all exactly the same. If I say task or activity, they're the same. But the project is all of these tasks have to be completed and finished. All right. So just a little bit more of the terminology. All right. This is how we're going to diagram our example. We're going to, all of our activities or tasks are going to be represented by a circle. And within that circle, the top part is going to contain the task ID. This can be a number or a letter or a name. And then below the bottom half of the circle is going to be the duration. How long does that specific task require to be completed? And so this whole process is called activity. We're going to be building an activity on node network, beginning with these circles. Then from that, we're going to use arrows or arcs. And the arrows here will represent the precedence relationship as shown here in this next diagram. So we've got two tasks, task A and task B. Task A has a duration of 6 days. Task B has a duration of 8 days. And what we say is since task A precedes task B, then task B cannot start until task A is finished. So whenever task A finishes, then task B can start, but only so A must be strictly finished, completely finished before B can start. So these are the basic symbols in our network. Okay. So now we're going to go and we're going to begin to build this network. And this is our information above. And the way that we're going to do this is we're going to lay out 7 circles, 7 tasks, 7 activities that have to be completed. 1 circle for each activity, 1 through 7. They can be anywhere on the page. They don't have to be in order. But then what is going to be important now is to describe the relationships in terms of the predecessors of each of these tasks, and we're going to use those to show the arrows. Now, one of the things I want you to notice is to be able to let's look at these predecessors, and how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 predecessors. And so when we get finished with our diagram, there should be 1 arrow for each one of these predecessors. All right. So let's first arrange these predecessors. All right. And so we're going to do this with arrows. And so what we'll see here is task 1 does not have a predecessor. So there's no arrow leading into 1. But task 2 must be preceded by task 1. And so we're going to represent that with an arrow from 1 to 2. And my line's not very straight, but I want you to, there's a couple of things I want to point out here. Number one, it's important to get the precedence relationship correct, but it's also important to have arrows on the end of your arcs or end of your lines, because as these networks get more and more complicated, you need to be able to understand exactly that 1 precedes 2. If this arrow were drawn line without an arrow, for example, let me just, if this were drawn without an arrow, then you might not be able to tell whether 2 was preceded 1 or 1 preceded 2. So those arrows are important. Okay. All right. So let's continue and go through building our network. You'll see here that task 3 is also preceded by 1. So we need to have then an arrow from 1 to 3. All right, and continue. Now, task 4 is preceded by both 2 and 3. So that means there should be an arrow from 2 to 4, because 2 precedes 4, and an arrow from 3 to 4, because 3 precedes 4. And then similarly for 5, both 2 and 3 precede 5. And so that takes us through task 5. And then task 6 is preceded only by task 5. So this is our arrow to task 6. And then task 7 is preceded by both 4 and 6. So we're going to indicate that with an arrow from 4 and an arrow from 6. And this completes our precedence relationships. And if you go back and count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 arrows, 9 precedence relationships, just as we expected. Okay, so that completes our tasks, that completes our precedence relationships, and now we're going to begin to do our work of determining how long it takes to complete the project. And we'll start that on the next slide. All right, so here's our example network again. I've cleaned up the arrows, and if you'll notice, I've added the durations associated with each one of the activities. So again, as you'll see, task 1, it takes 12 weeks. Task 2 takes 8 weeks. Task 3 takes 6 weeks, and so forth. Now this is going to, in order to do this correctly, there's a 3-step process. And the first step is we're going to calculate what's called the earliest start times, abbreviated ES, and earliest finish times, abbreviated EF, for each one of these activities. All right, and the way this is going to work is we're going to begin and we're going to start and ask ourselves the questions of when can task 1 begin? And just by convention, task 1 is going to begin at time 0, and that's the earliest time task 1 can start. Then we're going to ask ourselves the question, if it starts at time 0, at what time will it finish? And if it starts at 0, then it finishes at time 12, and that is our earliest finish time. And we're going to place those values, the early start, toward the upper left-hand portion of our activity, and our earliest finish time to the upper right-hand portion of our activity of our circle, as is shown here. Okay. So now we ask ourselves the question, all right, when is the earliest time that task 2 can start? Well, because of the precedence relationship, we know that it can't start until task 1 is finished, and that occurs at time 12. We cannot start until 12. And if it starts at 12, when will it finish? And hopefully you can see it'll finish at time 20, 12 plus 8. All right, so we'll always be able to say that the earliest finish time is always the earliest start time plus the duration of the task. Okay, always the earliest start plus the duration. All right, so now let's look at task 3. For task 3, when can it start? Well, it's preceded by 1, so the earliest it can start is when 1 finishes, which is at 12. And the earliest it can finish is, if it starts at 12, the earliest it can finish is 18. All right. Now we're going to get to task 4, and this is where I need you to think carefully. The question you need to ask is, when can task 4 start? Well, there's 2 alternatives for task 4. And one alternative is when task 2 finishes, because it precedes task 4. So task 4 can either start at time 20, but it might be, it's also preceded by task 3. So the question becomes, when can it start? And the logic is that you have to follow is task 4 cannot start until task 2 is finished, and it cannot start until task 3 is finished. If 3 finishes at 18, can task 4 start? And the answer is no, because task 2 will not finish until time 20. So therefore, task 4 cannot start until time 20. And the rule is for our earliest start times is as follows. It's the maximum, the rule for the earliest start is it's the maximum earliest finish time for all the predecessors. So it's the maximum value for all of the predecessors. All right. This is a critical point, so I want you to think carefully about that. All right. Similarly, now for task 5. Oh, excuse me, I didn't finish. If task 4 starts at time 20, the earliest it can start. When is the earliest it can finish? Well, that's going to be 20 plus 12, or 32 weeks. Now for task 5. When can it start? And similarly, it's preceded by task 3 and task 2. And so, like task 4, it cannot start until time 20. And if it starts at time 20, it'll finish at time 24. Now you'll notice here that it doesn't have to be exactly in the, in a specific place, but it's generally in this upper left-hand portion of the circle, because these arrows will get in the way, and you're free to have the flexibility to move those around a little bit. All right, so let's continue. Now we go task 5, task 6. When can task 6 start? Well, it cannot start until task 5 is finished. So that, therefore, it'll start at time 24 and it will finish at time 28. And lastly, for task 7, again, task 7 is preceded by task 4. It's preceded by task 6. And so both 6 and 4, task 6 and task 4 have to be finished. And so the last one to finish is task 4 at time 32. So task 7 cannot start until the earliest it can start is time 32. And if it starts at time 32, it'll finish at time 36, 32 plus 4. Okay, so now we've gone all through the network, and at this point, we know, you'll be able to see that our project will finish at time 36. So it's going to take 36 weeks to complete all of these tasks, but that's just part of the challenge now. The next thing that we want to do is we're going to work backwards through the network on our next slide, and let's see how this works. And this is all the information that we had from our previous slide. But now we're going to work backwards through our network to calculate the latest finish time and the latest start time. And the logic is, see, I've got an error on my slide. I'll correct that in a minute. No, that's correct. The latest finish time, the question you want to ask yourself is, when is the latest this task can finish and not delay the project? And so we're going to start on the right with task number 7, and then move back all the way to task 1 to calculate the latest finish and latest start times. So the first question, when's the latest task 7 can finish and not delay the project? Well, clearly it has to finish by time 36, otherwise it will delay the project. Now, if it has to finish by time 36, when does it have to start? Well, in this case, we're subtracting, so it has to start by time 32, and that's our latest starting, because it has to start. The latest it can start is by time 32. Otherwise, it'll take us more than 36 weeks to complete the project. And we're going to work this all the way back through. And now for task, let's look at task 6 and determine what's the latest time task 6 can finish without delaying the project. Hopefully you'll see that it has to finish by time 32, because it's succeeded by task 7. And so the latest task 7 can start is 32. So task 6 has to finish by 32. All right. And similarly, task number 4 has to finish by time 32. Otherwise, it will delay the project. And if it has to finish by time 32, it has to start by time, not 21, but time 20. All right. Now let's look down here. So let me move forward one or two more steps. I didn't finish with task 6, because if task 6 has to finish by time 32, then it has to start by time 28. Now, moving back to task 5. Task 5 must finish by time 28. Otherwise, it will delay, because task 6 has to start by time 28. And if it has to finish by time 28, it must start by time 24. Hopefully you're beginning to see the pattern here of how this is working. Next, let's go to, we've completed tasks 4 and 5. Now let's look at task 3. And this is, again, where you need to think a little bit carefully, because task 3 has 2 successors. It has task 4 is a successor. Let me start over here with the pointer. Task 4 is a successor because of the arrows, and task 5 is a successor. So the question you have to ask yourself is this: when must task 3 finish? When it's the latest it can finish and not delay the project? Well, again, there's 2 choices. Because it has to finish by either time 20 or time 24, because in order to not delay the project, it has to finish by the time one of these 2 has to start. So the question is, when is the latest it can finish? So if it finishes by time 24, that won't delay the project through task 5, but it will delay the project because this task 4 has to start by time 20. So in this case, what we'll see is that task 3 has to finish by time 20 in order to not delay the project. Now, I want you to think about that, because that's going to be, this is one of the key areas where students will have trouble. So think about this carefully, all right? Because again, the rule for establishing our latest finish time is that it's the minimum value of the late start times for all of our successors, all right? And that's the case. This is 20 here is the smallest of the 2 successor late start times of 20 and 24. Okay. Think about that carefully. All right. And so finally, if task 3 has to finish by time 20, it must start by time 14. And again, our late finish time rule is that it's always the latest, the latest start time rule is always the latest finish time minus the duration. Right. Next, we're going to go to task number 2. And the question is, just like task 3 that's succeeded by task 5 and it's succeeded by task 4. So again, those 2 values, we're going to choose the minimum, and we know that it must finish by time 20. And if it must finish by time 20, it has to start by time 12. And now we're back at ready to go to task 1. And again, task 1 has to finish. Again, there's two choices, either choose 12 or 14. That's going to be our latest finish time. And as you may see here, the minimum of that is 12. So it has to finish by time 12. And if it has to finish by time 12, it has to start by time 0. Okay. So that's the process of calculating a late finish and late start times. Now we're going to talk about, we're going to use this information on the next slide to determine the differences between two categories of these activities that we have to identify. So let's go to the next slide. All right, here's all that information cleaned up a little bit. Now you'll notice there's some tasks where the let me just start with task 2, where these latest start times and the earliest start and the latest finish and the earliest finish times are the same. Then there's other nodes, other activities where they are not the same. So the thing that you need to ask yourself, what does this mean? Why are these two different? And what happens is, in this case, hopefully the logic will make sense. This task number 2, the earliest it can start is 12, but the latest it can start without delaying the project is 12. So if there's any delay, the project is going to be delayed. So what that should mean, or what that does mean, in fact, is that task 2 is a critical task, right? And if you identify the activities where there are the earliest start and late start are equal and the earliest finish and late finish are equal, those tasks are on the critical path. I'll talk about that again in a minute. Let's identify those. So task 1 is on the critical path. All right, and that's critical. That path is critical. Task 2 is on the critical path. Task 4 is on the critical path. And task 7 is on the critical path. And so our critical path, in this case, is the critical path goes from task 1 to 2 to 4 to 7. That's our critical path. Now, what about these others? What about task 3, task 5, and task 6? What can you say about them? Well, let's take a look at task 6. All right. So let's look at the early start and late start and the difference between the earliest finished and the latest it can finish. You'll notice that in both of these cases, the difference here between these two, there's 4 weeks. All right. So the earliest task 6 can start is time 24. The latest it can start is 28 without delaying the project. So in here, there's 4 weeks difference, and that there's flexibility, there's float, if you will. Formally, we're going to call this 4 weeks of slack. And so there's 4 weeks of slack in task 6 because there's flexibility between these early start times and late start, earliest finish and late finish. And of course, that's the same for task 5, there's 4 weeks, and you'll notice for task 3, there's only 2 weeks of slack. But this tells you where there's some flexibility, whereas for tasks 1, 2, 4, and 7, they're on the critical path. Each one of these must be completed on time. And that the only way that you can determine this is by considering these early start and late start, making those comparisons throughout the network. Okay, so that's what we've done. So now we know that this house can be built in 36 weeks, and that tasks 1, 2, 4, and 7 must be completed on time, and that tasks 3, 5, and 6 have slack. So that's all what we've done to complete our network. So this is a summary of what we've done. We built the graph, we built the network. We started and we calculated our early start and early finish times through the network. We went from the end of the network to the front, and we calculated our latest finish and latest starting time. And then we went back through the network and determined the critical path where early start times equal the late start and early finish equal the late finish. And any other activities where that was not true, where they weren't equal, were activities where slack existed. Okay, so hopefully this helps. I'm going to end this video here, and we'll talk about project crashing next.